My name is Kat Medill, and my project was about subtask classification with eye gaze for teleoperated tasks. Teleoperated robotic arms, such as the one shown here, have become a great tool for individuals with disabilities to independently complete everyday tasks. However, these devices are often difficult and frustrating to operate. Although this video is sped up, it actually took this participant 2 minutes and 50 seconds to simply push the plate over. Assistive algorithms have emerged as a way to make these devices easier to operate, but they are currently only effective for one-step tasks. To develop assistive algorithms that are effective for multi-step tasks, it's important to know which immediate subtask the user is attempting. Since eye gaze is a natural behavior that indicates an individual's goals, we propose incorporating data about the user's eye gaze into an action recognition model to improve the classification of the subtask. This video demonstrates the food preparation activity that our work focused on. We identified 4 subtasks to classify. The subtasks are grasp spoon, scoop food, dump food, and push plate. Of the 6 pilot trials we used, 2 were completed in this order, and 4 began with the push plate subtask. As a starting point for our work, we chose to use an action recognition approach called the Compact Generalized Non-Local Model, or CGNL. This model is one of the more recent successful action recognition approaches in computer vision. We use the CGNL model without any eye gaze data incorporated into it as the baseline to compare our gaze featurization approaches to. We investigated 2 different ways to featurize eye gaze data. The first approach incorporated the raw X and Y position of the user's gaze into the final layer of the CGNL model. The second approach embedded the gaze data into the input frames by overlaying a dot at the position of the user's gaze. An example of one of the input frames for this approach is shown here. All 3 approaches, the baseline, raw gaze, and gaze overlay, were all trained and tested on 6 pilot trials using a 6-fold cross-validation method. The overall accuracy by trial and approach are shown here. For most trials, the addition of eye gaze data had a minimal effect on the overall accuracy, with less than a 1.75% change for trials 1, 2, 4, and 5 for both approaches. The accuracy of trial 6 decreased significantly for both eye gaze approaches, but we suspect that was due to calibration issues with the glasses used to collect the eye gaze data. For trial 3, however, the overall accuracy improved from 78.95% for the baseline to 88.47% with the eye gaze overlay approach, for an overall improvement of 9.52%. These timelines of the results for the baseline, raw gaze, and gaze overlay for trial 3 show specifically where the accuracy was improved when eye gaze was added. The baseline model especially struggled to classify the first subtask, grasp spoon, shown here. The results of the gaze overlay approach at the bottom, however, show significant improvements for the classification of grasp spoon. We suspect that the baseline model did not perform as well in trial 3 because it was one of only 2 trials that began with the grasp spoon subtask. We think the improvements shown in trial 3 indicate that eye gaze could be most powerful in improving the classification accuracy of subtasks that occur in a non-predominant order, therefore improving the overall robustness of the model. In the real world, users will not always follow the same subtask order, so it's important to be able to classify subtasks regardless of the order they're completed in. Future work should expand on this project by testing these approaches with a larger number of trials with a variety of subtask orderings. I would like to thank the U.S. Air Force Academy for sponsoring this work. I would also like to thank Rachel Burson and John Dolan for all their work coordinating the Summer Scholars Program, and thank Professor Henny and Monty and Maggie Collier for all their support and guidance throughout this project.